All right, open up your book to section 4-3. We're on page 188 in your book. Page 188, and the title of this section is Graphs and Zeros of Higher Degree Functions. Again, in particular, we're talking about polynomial functions. And the objective is, given a polynomial function, determine from the graph what the degree might be, and vice versa, and then find the zeros from the equation or the graph. We've kind of done a little bit of both of those here in the first half. We're going to continue that with the second half here. We're also going to look at a cubic function, some of its features in particular. Start off with the fundamental theorem of algebra. Fundamental theorem of algebra states the following. It says a polynomial function has at least one zero in the set of complex numbers. Polynomial function has at least one zero in the set of complex numbers. Now that one probably isn't as critical or as important to us as what the corollaries of that theorem state. And that's what FTA here stands for, by the way, the fundamental theorem of calculus. And there are two corollaries that come from that are definitely a very useful corollary. The first one here is an nth degree polynomial function has exactly n zeros in the complex numbers. And what that means, if you got a polynomial function, you can actually factor it completely into linear factors as long as you include complex numbers. So some of them might not be real, or we can actually factor it that way. And that's also including multiple zeros. So you can have zeros of multiplicity 2 or 3 or whatever degree that you need. The second corollary from the fundamental theorem of calculus says that if a polynomial has only real coefficients, then any non-real complex zeros appear in conjugate pairs. And actually, you've seen that now, that when we found the zeros of some of those polynomial functions, and they turned out to have a complex zero, it turned out the other complex zero was its conjugate. This only works if you're talking about a polynomial, though, with real coefficients, which for the most part, that's what we're going to deal with. But it is possible that you could have a polynomial function written where one of its coefficients is non-real, and then obviously this does not apply. But for all the polynomials we're going to deal with, we'll see that if we have a polynomial with real coefficients, then if we find a complex zero, its conjugate is also going to be a complex zero. We've talked about this property here. It's kind of a numerical pattern that we recognize with the number of our functions that we've covered at this point. And we've talked about the add property for a linear function that can actually be called a constant first difference. We've talked about the constant second difference for a quadratic function. You can actually extend that to any degree that you need for any polynomial function. So for an nth degree polynomial function, if the x values are equally spaced apart, then the y values will have a constant nth difference, is what you'll find. So that extends to a cubic function then, would have a constant third difference. Quartic would have a constant fourth difference, and so forth. Now, obviously, you got to have more and more data each time you go to a higher degree, so you can actually see if it's a constant nth difference there. But nonetheless, that's the property there for a polynomial function. All right. For a cubic function, if you have a cubic function, p of x, which is equal to ax cubed plus bx squared plus cx plus d, and you have zeros, z1, z2, and z3, then we have the following three things that are true here. The first one is that the sum of the zeros, that is z1 plus z2 plus z3, is going to turn out to be the opposite of b over a. Turns out that if you sum your three zeros together, it's going to turn out to be the opposite of b over a. If we take the pairwise products of our zeros and add those up, that is, if we take z1 times z2, and then z1 times z3, and then finally z2 times z3. So we're multiplying each zero by the other one. Turns out that's equal to just c over a. And the last one here is the product property there, that if you just take Z1 times Z2 times Z3, if you multiply your three zeros together, that's going to turn out to be equal to the opposite of D over A. Now we have similar properties for quadratics, by the way. In fact, we use kind of these same properties when we're trying to complete the square, for example, or when we're trying to work with quadratics and factor them. We use basically these same type of properties that show up with quadratics. This is extending it to cubics, though, and cubic functions, we're probably not as familiar with these properties here. All right, so let's take a look at an example here. Example 3 there on page 196. It says find the zeros of the polynomial function f of x is equal to, it's a cubic function. Let me write this function down. They gave us f of x is equal to x cubed minus 13x squared plus 59x. And then minus 87. All right, so there's our cubic function they've given us. It says find the zeros of that function and then show that the sum of the zeros, the sum of their pairwise products, and the product of all three zeros correspond to the coefficients of the equation that defines f function f. Okay, so let's first of all find the zeros of this function, and if it's a cubic function, they're going to have to give you a little hint to help you find your zeros, or else you're going to have to use your calculator to help you do that. And since they didn't give us a hint, we're going to have to grab our calculator. So grab your calculator, and let's see if we can find at least one zero to help us get going with this. All right, so with your calculator, let's put into y1 this function they've given us here. So they gave us x cubed minus 13x squared plus 59x minus 87. All right, and let's go to our window. Actually, I'm just going to graph this in the standard window. I might not get a good sketch of what this cubic function looks like, but remember, I'm only worried about finding zeros, so I really only care to see where it crosses the x-axis. So let's see if we can see it cross the x-axis. Hey, there we go. We're in business. There's a 0 there. It looks like it's right at 3, but let's find that for sure. If you go to your second calc menu, there's an option here to find zeros, and these are actually real zeros we're going to find. Let's give it a left bound of, it looks like if we go from 0 to, I don't know, 0 to 5 here, I'll give it a right bound of 5, and I give it a guess of, it looks like it's at 3 that zero's at. Hey, and it is right at 3. I guess we could have traced it there to find that as well, but this actually tells me the zero's at 3. Okay, so we did find 1 0 with this. Let me grab a picture of that. All right. So remember that once you find one of its zeros, you've actually found one of its factors. So that actually helps us out a lot. That I can actually write this as x minus 3 times some quadratic factor here. All right. And to find that quadratic factor, probably synthetic division is going to help you out here. You can actually do this without using synthetic division. It's not real easy to do, but you can use a couple of properties that we know here. I know that when I take this quadratic term here, this x squared term, and multiply it by x, I have to get an x cubed. So that tells me that this must be an x squared here in order for that to happen. And likewise, when I take this negative 3 here, and I multiply it by this constant over here, again, there's going to be 3 terms in this quadratic on the right, that has to give me a negative 87. So that sounds like positive 29 would do that. If it was 90, then 3 times 30 would give me 90. So let's put a plus 29 there. And now I just have to figure out the x term in the middle. And there's actually 2 ways you can go about doing that. I'll show you one of them, but you could either use the x squared term or the x term to do it. I'm going to use the x squared term only because that's a smaller number here. It's a negative 13 versus dealing with the 59. So this term right here, the negative 3 times x squared, that's going to give me half of my x squareds. And then I'm going to have to multiply this x term here out front. Maybe I should do that in another color. this x term out front has to get multiplied by this x term here that I'm going to fill in to give me the other half of my x's. So together, those two have to total the 13x squared that I see up above. So I already have a negative 3x squared that I've underlined down here in blue. I need another 10 of those, actually another negative 10 of those. So this must be a minus 10x. Again, you can factor that, like I just went through with you. That's a little more complex. If you don't like that, then let's run that through our synthetic division or synthetic substitution here. Put your 3 out front. Write your coefficients. It's 1x cubed and negative 13x squared, 59x, and a minus 87. So bring down your 1, multiply by 3, add negative 13 to that, it's a negative 10, multiply by 3, that's a negative 30. Bring that down, that's 29 times 3, that's going to be 87. Not 89, 87, and that's going to give us our 0 then, right? And double check our answer here. We've got 1x squared, we've got a negative 10x, and we got a positive 29. Yeah, that checks out. That's what we got up above there. All right. And now with this, if this factors nicely, which it doesn't look like it's going to do. In fact, when I look at the sketch over there, it doesn't look like it crosses the x-axis any more times. So the other zeros must be complex zeros. So if we want to find the other zeros, it looks like we're going to have to go to quadratic formula to do that. So let's find the other zeros here. So I'll take the 10, the 1x squared, the negative 10x, and the 29 is what we're going to plug through our quadratic formula. So x is equal to the opposite of a negative 10 is 10, plus or minus the square root of b squared is 100, minus 4ac, so 4 times 29, that's 80, and 36 is a 116, I think. That's our problem right there. There's your negative number that you're taking the square root of, all over 2a. So what's this simplified to? Well, we've got 10 plus or minus, that'll be the square root of negative, oh, that turns out to be actually not too bad, since it's a perfect square that I got underneath there. So I could write this as 10 plus or minus, square root of 16 is 4, and the square root of negative 1 is I. That's how I could simplify that. In fact, that even simplifies nicely. The 2 will divide into the 10 and the 4 there, so I could write this as 5 plus or minus 2i is our other two zeros. So there's our 3 zeros that we have there. X equals 3, x equals 5 plus 2i, and x equals 5 minus 2i. So if we take f of x and we set it equal to, or rewrite it as x minus 3 times x minus, I'm going to put this in parentheses, 5 minus, let's do the plus 2i, I guess, first. And then x minus 5 minus 2i. By the way, notice with those two complex zeros, they look alike, look very similar, I should say. They're complex conjugates of each other. This is what we just talked about with that fundamental theorem of algebra, actually one of the corollaries of it. All right, part 2 of this one said, then show that the sum of the zeros, the sum of the pairwise products, and the product of the 3 zeros correspond to the coefficients in the equation that defines function f. Okay, so we'll call this part B. Part A is what we did up here. All right, part B. Let's find the sum first of all. So for the sum, we're just going to add up our 3 zeros. So it was 3, it was 5 plus 2i, and 5 minus 2i. Well, that actually turns out to be pretty nice there. Notice the imaginary parts are going to cancel each other out. And what do you end up with here? You end up with 3 and 5 is 13, it looks like. According to our property, this sum should be equal to the opposite of b over a. And what was b again? I got to go back up to my original equation. B was a negative, oh, there we go, negative 13. So we got the opposite of a negative 13 divided by a is 1. Yeah, this turns out to be 13. These are, in fact, equal to each other. The sum of the zeros and the opposite of b over a are the same. All right, let's do the pairwise products. I'm just going to call these the pairwise. Actually finding the sum of the pairwise products, but so we'll take 3 and multiply it by that first 0, 5 plus 2i, and then we'll add it 3 times the other 0, 5 minus 2i, and then we got to multiply our 2 complex zeros together, 5 plus 2i times 5 minus 2i. I know since those are complex conjugates, those will actually turn out to be pretty nice to multiply together. So what do we end up with here? We have 15 plus 6i. Here we'll have another 15, but minus 6i. That's nice. Those are going to cancel each other out. And over here, since we've got complex conjugates we're multiplying together, there's no imaginary part going to show up from that, right? We end up with 25, and then it's going to be, when I take the I squared and replace it with a negative 1, I'm going to end up with plus 2 squared is 4. So again, the 6i's cancel each other out. These guys here are gone. All you're left with is real numbers. So 15 and 15 is 30, and 25 is 55, and 4 is 59, it sounds like. So this is equal to 59. I'll just write it over here. All right, and so we said that the pairwise product should be equal to C over A. So C over A, I got to go back and refresh my memory on what value C is. C is, 59, check that out. C over A is 59 divided by 1, which of course is 59, so yeah, those check out. Those are the same. The sum of the pairwise products turns out to be equal to C over A. And then finally, let's deal with the product. So we'll just multiply these three together here. So I've got 3 times 5 plus 2i times 5 minus 2i. We've actually already multiplied the conjugates together, so let me do that first. So that turned out to be 25 plus 4. 25 plus 4 is 29, and if I multiply that by 3, that's 60, and 27 is 87. Is that what I end up with? 87. So we said that if you find the product of those, that product should be equal to the opposite of D over A. A we already have as 1. What's the value of D? D is a negative 87. That's nice. So we have the opposite of a negative 87 divided by 1. The negatives cancel out. Dividing by 1 doesn't change anything. Yeah, those turn out to be the same. The product of our zeros does, in fact, turn out to be the opposite of D over A here for this problem. Very nice. And then show those are that. Yeah, that's all they want us to do there for that one. All right, so let's take a look at one more example. Example number 4. So let's find the particular equation for a cubic function with integer coefficients if the function zeros have the given sum product and sum of pairwise products. So they're giving these three values we were just playing around with in the previous example. Confirm these properties after finding the zeros of the function. All right, so we have to have a sum has to be equal to a negative 5 over 3. We have to have a pairwise product. I'm just going to go ahead and call it pairwise here. It's the sum of the pairwise products, I know, but that turned out to be negative 58 over 3. And then finally, the product of the zeros has to be equal to 40 over 3. All right, so remember that your sum, I'm going to just write down what each of these are equal to. The sum, we said, this is equal to the opposite of B over A. The sum of the pairwise products was equal to C over A. And the product was equal to the opposite of D over A. So you can pick whatever value of A you want to use here. If it looks like it's a nice number here, which is what I've got, then I'd pick the obvious value here. A is the value in the denominator, and since all of these denominators are 3, I'd pick that as my value for A. All right. If it turns out that you end up with an equation that doesn't have an integer coefficients like they want here, then I can multiply that by whatever I need to get rid of the fractions. But I think here it's pretty obvious that I should pick A as equal to 3. So that's what we're going to do. So if I make A equal to 3, well, then I guess the rest of this is going to be pretty straightforward, right? If the sum is equal to a negative 5 over 3, where A is equal to 3, that means that the B must be 5. Moving on to the next one, if, again, I'm making A equal to 3, so if the opposite of 58 over 3 is C over A, that means C must be the opposite of a negative 58. There must be a negative 58. And for the product, again, A is the 3 there, so this is equal to the opposite of D over A. So it must be the case that D is the opposite of 40 then. again, plug in those values and double check that that works there. But that looks like a pretty straightforward answer there. If these, by the way, didn't have all denominators of 3, one way to do this would be just to pick a value for a, like make it 1, and then go through the same process. Or get a common denominator might be a better first step, and then picking that as your value for a there. But anyways, what do we end up with here? We have, did they give us a name for this function or not? They did not. I'm going to call it f of x then. So f of x is equal to, it's going to be 3x cubed plus 5x squared minus 58x minus 40. Looks like our equation here for f of x. And again, they wanted integer coefficients, so that's what we got here. And then they said find a particular equation, all right. Confirm these properties after finding the zeros of the function. All right, so I guess we're going to have to take that equation there. They didn't give us any hint as to what the zeros are. They told us what the sum and product and so forth are, but they didn't give me a hint on any one of these. So let's do the same thing. Grab our calculator and plug that into y1 and graph this thing. So grab your calculator. All right, so on our calculator, let's change what we have in y1. So let me just get rid of that here, and let's punch in the equation that we came up here with. Here it was 3x cubed plus 5x squared minus your 58x and minus 40. All right, make sure you got the right equation in there. And again, we're just trying to use our calculator here to help us find some zeros. So I really don't need a good sketch of this. You could, worry about the window that you got here, but all I need to do is see it cross the x-axis. As you can see here, I've got 3 real zeros, but it's not necessarily the best sketch, but that's okay. We don't need a great sketch to be able to find our zeros. Let's just find well, actually, we can easily find one of these. I guess let's do that, and we'll find the other 2 another way. So let's find that 0 that's on the left side here. So I can calc. It looks like it's at, what, 1, 2, 3, 4, 5. It looks like it's at -5. So let's go from -6 on the left side to -4 on the right side. And we'll give it a guess of -5. Hopefully that's a nice number. It is -5. Very nice. Okay, so -5 turns out is one of our zeros. Grab a picture of that. All right, so we found one of our zeros. And again, once you find one of the zeros, you can, let me just slide this over here. Once we find one of those zeros, we can use that to factor this thing. So I have f of x is equal to x plus 5. Again, if you want to use synthetic division here to find the other zeros, then go for it. Or the other factor, I should say. But I think we can probably factor this here. I know I got to have a 3x squared, or 3x cubed here, so it's going to have to be a 3x squared here. And I have to have a -40, so that means I got to be subtracting 8 here. And now for the middle term, I'm going to use the 5x squared. I've already got a 15x squared here, so I need to subtract off 10 in order to end up with 5x squared there that I want. So I should have 3x squared minus 10x minus 8. And if that factors nicely, I need 4 and 2. Might need to use synthetic division on this, although it does look like it's got a nice 0 over there. Well, it's not obvious here. Oh, that's because I got a 3x squared. Oh, I think we can still factor this. Let's try factoring this. This one might be easier to grab your go through synthetic division to find the factors here, but let's see if we can do it without synthetic division here, just for a little practice of factoring. I have to have x and 3x in order to get my 3x squared. To get a value of 8, I need 2 factors like 2 and 4 or 1 and 8, I guess are my 2 options here. And if I multiply my 3x times 4, that'll give me 12. If I make that -12, I can then do a plus 2, I think, and get the other 2x that I need. Double check this here. So I've got 3x squared, I've got a minus 12x, and then I have a plus 2x, so that'll give me a -10x overall, and then a -8. Yeah, that does factor nicely there. Okay, so This is what we end up with. All right, so what do they want us to do now? Find the particular equation, find the zero. So I guess to set this equal to 0 and solve that, we'd have x is equal to a -5. Oops, x is equal to a -5. You're taking x minus 5 and setting equal to 0. I started to write that, but then I'm just going to write down our zeros here. X is -5. X is equal to a +4. And then if I set that one equal to 0, I'll subtract the 2 and then divide by 3. That's a -2/3. You might want to double check that on your calculator there, but that does look like where I'm crossing the x-axis over here in my sketch. It's somewhere around a -2/3, so that looks good. And so they want me to calculate the sum and the pairwise products and so forth of these and compare that with what they gave me, I guess, in the problem. So let's do that. So let's start with the sum. We'll have a -5 plus 4. And then plus a -2/3, or -2/3. So -5 and 4 is going to give me a -1. And then subtracting 2/3 is a -5/3. Hey, that sounds like the number they gave us there, right? -5/3, yes. Nice. All right, 1 down, 2 to go. Let's find the pairwise products. So take a -5 times a times a +4. I'll put these in parentheses. We'll add that to a -5 times the -2/3, and we'll add that to the 4 times the -2/3. Make sure you've multiplied each of the zeros there by the other 2 at some point in time here. So what do we end up with? A -20 here, +10/3 there, and then a -8/3 over here. So we have a -20. 10/3 minus 8/3 is going to give me 2/3. Maybe it's actually going to be easier to write these all as thirds, right? -20 is a -60/3 plus the 10/3 minus the 8/3. And what does that give us? So on the numerators that I've got to deal with now. So I've got a -60 plus 10 is a -50, and minus 8 is a -58/3. That does sound familiar too. Up there and double check what they, yeah, -58/3 is what they told us. Sweet. One last calculation here. Do the product. So if we take the -5 times the 4 times the -2/3, what do we end up with? So a -5 times a -4, that's going to be, or times a +4, that's a -20 times your -2/3. And -2/3, just multiply the numerators there, right? So it's 40/3 is what we should end up with here. So we had up above 40/3. Nice. There we go. Turns out that those all three check out here. We end up with the sum, the pairwise products, as well as the product. They're all giving the same value that they gave us originally. All right, and that's the end of the second half here of section 4-3.